Hello, my name is Omba Serrano, and I'm very happy to be here today presenting the work Logistic Q-Learning that we, together with Sebastian, Andreas, and Gergely. In this work, we present a new reinforcement learning algorithm based on minimizing a new loss function, the logistic Bellman error, that we present also as an alternative to the very well-known square Bellman error, because the logistic Bellman error has better properties since it's convex, smooth, Lipschitz, and derived from first principles, which are properties that the square Bellman error doesn't have, as it's illustrated in this plot here in the bottom left, where we can see different loss functions as a function of the Q value for a given state and action pair. And we can see that the logistic Bellman error behaves very nicely, while the square Bellman error and the Hoover loss have local minima. We work in the framework of Markov decision processes, where a learner or an agent interacts with a Markovian environment in the following way. At each time step, the learner observes a state, picks an action, receives a reward, and travels to the next state according to a transition kernel. And we work in the standard setting of discounted MDPs, where the goal is to maximize the discounted reward return that we have in the blue box. So let's start from the beginning, the square Bellman error. The square Bellman error is a loss function that measures how good a Q function is as a solution to the Bellman optimality equations. And in minimizing the square Bellman error, the DSB is used as an heuristic for finding approximate solutions to the Bellman optimality equations. Despite its broadly used, it has some shortcomings, and it's not very well motivated by theory. Some of the properties that are not very good that we have already seen is that it's non-convex, non-smooth, and non-Lipschitz, and that it's hard to estimate due to a sample issue known as double sampling issue. There are some ways of patching DSB, like target networks to break down convexity, and double sampling, gradient gripping for unbounded gradients, or other tricks. But in this work, what we will do is to present a well-motivated alternative, which is the logistic Bellman error. Despite these bad properties that we have seen that the Bellman error have, it's almost everywhere. So every reinforcement learning algorithm has the square Bellman error somewhere. We can find it in deep Q networks, in policy gradient and actor critic methods, TRPO, PPO, MPO, and others. So let's present the logistic Bellman error that we have here. And the logistic Bellman error comes from a regularized linear programming formulation. And the name, logistic Bellman error, comes from the fact that it's very similar to the logistic loss that we find in classic machine learning for supervised classification. In the expression that we see in the screen, we can see that we have a mu, that is the state action occupancy measure. We have two parameters, eta and alpha, that are parameters of the loss. Actually, alpha is not displayed in this first expression because it's inside the delta that we see there. That is the Bellman error. And we also have this B sub Q, which is the value function that is a softmax value function, so we can compute it using Q. So the logistic Bellman error is only a function of Q, of the Q function. The good news are that this loss function is convex and smooth. It's to Lipschitz with respect to the L infinity norm, and it's easier to estimate than the square Bellman error via samples, as we will see in some slides. Then, using this loss function, we present the following algorithmic scheme. First of all, we have to say that here the Q functions are linearly parametrized. So they are the inner product between a weight vector, theta, and a feature vector, phi, that is defined for every state and action pair. In this Q-reps algorithm, we start with a policy pi 0, and then it works in iteration. And in each iteration, we have two steps. The first step is policy evaluation, where we compute the weights that parameterize the Q function by minimizing the logistic Bellman error. And then, the logistic Bellman error corresponding to the distribution mu k. And then we update the policy using an exponential update using the Q functions that we found in the policy evaluation, and we keep iterating. Then, since we want our algorithm to be able to work in the reinforcement learning setting where we don't have access to the model, we need to be able to work with sample transitions. That's why we define the empirical Lve. First of all, let's define the TD error, which is like the Bellman error, but for a sample transition, where we substitute the expectation by the value function of a sample transition. And we assume that we have a collection of sample transitions that have been extracted or drawn from the distribution μk. In practice, what we do is to run the policy PyK in order to gather those sample transitions. In the yellow box, we have the empirical logistic Bellman error, LVE, and we see that it's like the LVE, but we have substituted the one of the expectations by an average over sample transitions, and the Bellman error by the TD error. The problem here, as it's set in this warning box, is that we have bias. So this estimator is a biased estimator, and this is because the Bellman error has an expectation inside, and as we know, the expectation of an exponential is not the same as the exponential of the expectation. That's where the bias comes from. The good news are that we have a way of controlling it that we will see in the next slide. This bias, I mean. Okay, so performance guarantees that we show in our work. We have like two parts here. We have divided it into parts because we have two theorems, and each theorem addresses a different question. The first theorem addresses the question, how serious is the bias? This bias that we have just seen. And the answer is that it's not too serious, as we can see in theorem 1, where we see that the bias is of the order of the sum of two terms, where the second term is negligible when n is large enough and n is the number of samples. And the first term is the parameter of the loss function eta. So the takeaway conclusion is that we can control the bias using eta. And this is a result that is impossible for the square Bellman error. About theorem 2, it faces the problem that practical implementations have always optimization errors. And since we work in different rounds, it's interesting or it's necessary to know how do these errors accumulate. And the answer is that they accumulate very reasonably, as we can see here in theorem 2, where we see that the errors accumulate linearly. We can also see here in this theorem 2 that for if the errors are 0, then our algorithm converges with a rate of 1 over k. Another thing that we can extract from theorem 2 and 1 combined is that for large enough n, and if we set alpha and eta appropriately as 1 over square root of t, then we get a rate of convergence of 1 over square root of k. Finally, we show a way of minimizing the LVE, the ELVE. That is how we have done it in the experiments, and it's based on this equality that we have here in the yellow box, saying that minimizing the ELVE, the empirical logistic Bellman error, is equivalent to solving this min-max problem that we have below, where we have a new set of variables, z, that are a distribution over sample transitions. So as we can see here, now the gradient with respect to theta is an expectation, since theta is a distribution. So it's very well suited for stochastic gradient descent. And actually, the algorithm that we have used for implementing the QReps is a two-player game between a learner that updates theta via stochastic gradient descent and a sampler that updates the distribution over samples, over sample transitions, via exponentiated gradient descent. And it works. We have here the results of the experiments where we tested our algorithm QReps in different domains and compared its behavior with the behavior of other state-of-the-art algorithms like DQN, PPO, Reps, or BMPO. And as we can see, the results are very good, and QReps performs very well. Okay, finally, what's behind QReps? QReps is inspired by Reps, which is a work from Jan Peters et al. From 2010. It's based on the LP formulation of MDPs. And when we have seen the algorithm QReps, at each iteration, actually what we're doing is to solve this convex problem. Actually, the logistic Bellman error is the dual of this primal problem, and it's an unconstrained dual. That's why we tackle this problem instead of this other one. If we look at this convex program, what we can see is that we have different colors. This is because the black part, the black terms, correspond to the classic formulation of linear, so the classic linear program for solving MDPs. The blue part is some regularization that we add. The yellow part corresponds to a Lagrangian decomposition of constraints that make Q functions appear, and this is very important. This is one of the key points of our work, because in Rep, for example, they don't have this part, and then they have to work with value functions. And it makes much more difficult the part of policy update. And finally, the red part corresponds to a linear relaxation of constraints that makes Q functions to be linearly parameterized. Finally, the analysis is based on mirror descent analysis, stability analysis for MDPs, and properties of entropy regularized MDPs. And that's it. Just to say that we are very happy with the results of this work, and we hope that this brings new opportunities for reinforcement learning algorithms. And we really believe that the logistic Bellman error could be a key tool for future algorithms. Thank you very much for listening, and we strongly encourage you to visit our poster and read our paper. Thank you very much.
So I do have one question, which is that are there some settings under which the logistic Bellman laws versus the squared laws, they are similar to each other, or they are consistent with each other?
Yeah, that's a great question. So hey, I'm Gergely. I'm sitting here with John. So actually, as these step size parameters, these eta and alpha, they go to 0, then these losses become very, very similar to each other, because basically then the exponential function in this log sum approximates the squared loss very nicely. Well, it's going to be like a scaled version of the squared loss. So for very small step sizes, the objects become very similar. And actually, there are algorithms that use the squared Bellman error and exponential updates for small learning rate parameters. These are known as polytax conversions. So you could think of those as generalizations of what we do here. This is the way that we prefer to think about this. But we really believe that this logistic Bellman error is somehow the more fundamental object of these.
Very nice. There are no other questions. So let me ask one more question, just curious. So in the end, for the QReps, you mentioned that you can get analysis using mirror descent. So what are roughly the rates of convergence that you get typically there? Are these standard?
Right. So this is basically mirror descent on a fixed linear function, which is if you implement the updates without any errors, that converges at a rate of 1/k, k being the number of iterations, number of updates. And we actually do recover that rate if you don't have any optimization errors. One of our main theoretical contributions is understanding how the optimization errors propagate. So what happens if you cannot exactly implement the updates and you have these epsilon errors in the evaluation of the Bellman error. And actually, it turns out that these errors propagate very reasonably. They just accumulate linearly, and there's no explosion that's happening.
Okay.
Yeah, so I guess the short answer is we have a 1/k rate there.
1/k. Okay, thanks. One final question from Tiago. It's how does the logistic Bellman error behaves with continuous action space?
Okay. Continuous actions. So, well, I guess this whole algorithm template that we are showing here, it does generalize to continuous actions. I guess picking the right policy parameterization for continuous actions is the tricky bit. Typically you would have to work with Gaussian distributions over the actions. So I think that as a design principle, things should work out very nicely. I'm not sure how the performance guarantees would look like.
Okay. All right. So thanks so much. This was quite fun. Thanks, John and Gergely.